Hello, in this lecture, we're going to start talking about a new functional group, just ever so briefly, as it kind of veers us into the next major topic in the course, which is resonance. So that functional group is called the allyl functional group. So the allyl functional group is, it's actually kind of awkward to call it a group. It's a little bit better to call it a position. A position. Okay, so it's just sort of a special carbon atom in that the carbon atom is next to an alkene. Okay, so what does that look like? Well, if we have an alkene, what we want to do is consider these atoms that I guess I've highlighted with like or circled around with a home run or a home plate in baseball. So it's the carbon and the two hydrogens. This is the allyl carbon and the allyl hydrogen atoms. And so those are what I think we should focus on. However, if we are going to talk about the functional group, we would say that this whole thing with the alkene, the allylic carbon along with the alkene, that is the allyl functional group. And you're like, wait, isn't that just an alkene with a carbon? Yes. That's why I say it's actually a little bit more helpful to pay attention to the position as opposed to the actual functional group. So again, what we want to focus on is the run-of-the-mill sp3 carbon attached to an alkene. So we want it to be an sp3 carbon. That is, kind of your typical carbon tetrahedral. It's got 4 atoms attached to it, no double bonds, that sort of thing. So if we look at some examples, here's a really good starter example. It turns out that the allyl position that we care about is right here. This is our allylic carbon because it's a carbon atom, a CH3 in this case, next to an alkene. This and this are not allyl carbons because they're sp2. Okay. Now we can put other functional groups onto that allyl carbon and we get interesting molecules like this is, if we look here again is our allyl carbon, that carbon next to the alkene. And this molecule is called allyl alcohol. And if we have like a halide, like a bromine, we can highlight again, and this is allyl bromide. Whereas we have, once again, our allyl carbon and its associated elements. So it's not the alkene, it's the carbon next door to the alkene. Now, why do we care about this so much? It turns out that the allyl carbon is more reactive than a typical carbon. I need to make some new pages. Sorry, I had forgotten about that. Okay, so let's look at some more specific details about why the allyl carbon is more reactive than a typical carbon. So if we look at the allyl functional group, I'm going to pick on one of the hydrogens attached to our allyl hydrocarbon, and I'm going to point out that its bond is fairly weak. And we can quantify that by saying its BDE is 87 kcals per mole. Okay, so, and again, let's just, before we move on to the things we don't know, let's highlight the fact that this is our allyl carbon. And so I've picked an allyl hydrogen off of it to talk about. Now let's take a second to remind ourselves what BDE is. BDE is bond dissociation energy. Bond dissociation energy, and this is the energy required to break a bond by homolysis. Okay. Energy required to break a bond by homolysis. And so homolysis, this is our bond breaking event where both sets of atoms that were once bonded together have the electrons. And so if we have A bonded to B, we do a reaction, they could undergo homolysis and one electron goes to either side, and we could use fishhook arrows to show the movement of one electron, and we get two free radicals out. So what I'm saying is if we take our molecule, it turns out that this molecule, this hydrocarbon, is actually called Alane, and we pump 87 kcals per mole of energy that it can absorb, we get a free radical on the allyl position plus a hydrogen atom. A hydrogen radical. Now for reference, if we want to look at some other BDEs, now I'm saying 87 kcals per mole is actually low. Okay. Now for reference, and let's emphasize this first. Low BDE equals a weak bond. And why is that? Well, because it takes less energy to break that bond then. If it takes less energy to break anything, whether it's a chemical bond or whatever you can think of, we tend to say that that's weaker. It's not strong. Stronger things take more energy to break, and that goes for bonds as well. So I'm saying that 87 kcals per mole is low, and so it's a weak bond, that carbon-hydrogen bond. But I haven't given you a reference point yet. You're just sort of taking my word for it. Right now, the 87 kcals per mole means nothing to you. So let's get some reference in there. Unless you're familiar with all these BDEs, then it means everything to you. Okay, anyway, you probably don't. That's okay. So let's take ethane, for example. It turns out that if you want to snap this bond in half by a homolysis event where we push electrons to either side to give this species, this would require 101.1 kcals per mole. And just to emphasize here, that energy that I'm putting in, that's my bond dissociation energy, my BDE. So 101.1 kcals per mole for a run-of-the-mill alkane gives you a nice reference point. So we're going from 101.1 to 87. So, about 14 or so kcals per mole difference. And so that's why we say that's low. I mean, you're not going to go down to like 1 kcal, and things probably wouldn't even want to be bonded to each other. They definitely wouldn't. Okay, so we drop significantly when we go to the allyl system. Now, why do we drop, or why is this one higher? This is higher because the radical is primary and unstable, right? We don't want primary radicals. Anytime we have an electron deficient center, whether that's a radical or a cation, we want that to be more substituted because then it's more stable. Well, wait a second. Let's look at some more stable radicals, okay, that we could form. How about we take the central carbon-hydrogen atom of propane? Well, it turns out that to cleave that in half, to get the two free radicals, you would have to supply 98.5 kcals per mole. So you can see that this bond association energy is dropping as we go to something that results in a more substituted free radical. So there's our hydrogen radical along with now a secondary radical. Whereas earlier we had a primary radical. So we go from 101.1 to 98.5, about 3 kcal difference just going from primary to secondary. But we all know that tertiary are the best radicals. So what does the bond association energy look like for maybe a T-butyl group? So to break this bond, you have to supply, my notes say 96.5 kcals per mole. And that will break this to make a tertiary radical. These are the best radicals. Plus H dot. So we go from primary at 101.1, secondary at 98.5. So we drop 3, and then we drop 2 to go down to tertiary radical. And I always emphasize the tertiary radicals, tertiary electron deficient centers, radicals, and cations are kind of the best we can do. Okay, we get a really nice and happy radical. So there's our perspective. 101.1 is as high as, I mean, it's pretty high, okay, for a carbon-hydrogen bond. But then for a really weak carbon-hydrogen bond, that is a something that results in a T-butyl radical right here, or a tertiary radical, we get a weak carbon-hydrogen bond at 96.5. Now that's all to give you that frame of reference that the allyl group is very reactive. If we go back to allyl, that number I said for this carbon-hydrogen bond was 87 kcals per mole. 87 kcals per mole. So that's 9, almost 10 units or 10 energy units lower than forming a T-butyl cation, which is impressive because technically if you ignore the rest of the structure, I'm going to say it looks, because it's not entirely true, but it looks like a primary radical is being formed when you do a homolysis reaction of an allyl system. So this is all quite surprising. Now what it says is the allyl hydrogen is much easier to remove. Because the CH bond is weaker. And if the CH bond is weaker, anytime you have weaker bonds, you have a more reactive molecule. Okay, so that is our perspective walking into the allyl system, starting with the radical. But there are, as I've alluded to, other electron deficient centers that we could consider, that is carbocations. So what about those? Well, if the allyl radical is stable, it turns out that the allyl carbocation is also highly stable. Highly stable. So if we draw the allyl cation, I'm going to say that it's quite stable. And you're like, wait a second. I'm concerned about this. You're putting a positive charge on an unsubstituted carbon. I mean, a singly substituted carbon. This looks primary. Well, this is when kind of the rubber meets the road in terms of understanding that this is not a primary system. This is an allyl system. This is an allyl functional group. This is not a primary carbocation. So I'm going to say why. Well, it's first of all not a primary carbocation. I realize that so far we've defined primary carbocations as those that have a carbon, positive charge, and then one thing attached, the rest being hydrogens. Okay, that's certainly the case here, but this isn't a primary carbocation. What is it? It's an allyl carbocation, or sometimes this is called allylic, or an allocarbocations. Now, why are these allyl systems so stable? And let's specify radicals and cations. So why are allyl radicals and allyl cations so stable? Well, one of our favorite answers, and by we, I mean organic chemists, is the idea of what's called resonance. Okay, so we're going to start talking about resonance tiny bit in this lecture, but then we're going to pick it up, and it's actually going to be the focus of one of the computational labs, is thinking about resonance structures. But what we're getting at is something that we had touched on in the last module, and that is resonance structures. And I'm going to continue to evolve our definition of this over time, but these resonance structures are different depictions of the same molecule. This is an important concept to just ingrain deeply in our thinking about organic chemistry. These are different depictions of the same molecule. Okay, they're different structural depictions, but they describe the same overall structure, the same molecule, the same kind of composition and orientation and everything of matter. Okay, these aren't isomers of each other. They're just depictions, just structures. Isomers are actually different kind of ways that a single composition of matter can be arranged. Okay, so it turns out that, yes, this is true. And resonance structures differ in their distribution of electrons. So they differ in their distribution of electrons, not their distribution of nuclei. What this is saying, and I'm going to continue to emphasize this point over and over again, because this is an important point, but you probably won't grasp it as well as you will once you're better at drawing resonance structures. So not nuclei positions. That is to say, the atoms don't move, just the electrons kind of move and get redistributed. Okay, but the important point is that first point right now, different depictions of the same molecule. Another really important kind of intuition to have is that more resonance structures leads to more stable molecules. So what this kind of implies is that being able to draw a molecule in multiple resonance structures this leads to increased stability. Of the molecule. So if the molecule can be drawn as multiple resonance structures, it's going to be a more stable molecule. Okay, so I just want to keep emphasizing this. Different depictions, same molecule. More resonance structures, more stable. Okay, with that in mind, let's go ahead and start to draw resonance structures of our allyl system. So here is an allyl cation. Now what you can do, we'll use our double-headed arrow to show resonance, is we can actually also depict this resonance structure as having the positive charge on the left side. Okay? So these two are two different resonance structures, same molecule. So these are two different resonance structures, same molecule. Now I know some of you are saying, wait. If I rotate the left side 180 degrees, I can get to the right side. So these are duplicates. And Willoughby says, cross out your duplicates. That's when we're looking at isomers, different arrangements and compositions of the same matter, particularly constitutional isomers. Different arrangements of the same composition of matter. I have to say that correctly. Okay, anyway, that's with constitutional isomers from organic 1. Here, resonance structures were showing a different distribution of electrons. On the left side, we have the double bond extending between the left 2 carbon atoms, but on the right side, we have the double bond extending between the right 2 carbons. Now we can show that the electron deficient center is on the left side and on the right structure, and the right side and the left structure. So we have two structures to describe the same molecule. And now I can start to emphasize again, these aren't duplicates, because in duplicates, the nuclear positions don't move. Your atoms don't move. So to get from one side to the other, I'd have to do that flip. That flip moves the atoms. It moves the left side atom over to the right. I can't do that. I can only redistribute the electrons. I can only move the pi bonds around. The key takeaway here, and we're going to get good at drawing resonance structures. The key takeaway is we have more than one resonance structure. We have two. More than one resonance structure. I should like write legibly, sorry. We have two. Great. What that means is that we have more stability than expected. Why do we have more stability? Because we can depict the molecule in multiple resonance structures. Okay. So we have allyl cations. It turns out there's another functional group. We have these dimethyl allyl cations that can also be depicted as multiple resonance structures. And I like to put little brackets around my resonance structures to imply that these are describing the exact same molecule. This is actually called the prenyl cation, where prenyl is a fancy allyl group. Now, it's fancy because it has these two methyl groups, but prenyl's also got a lot of interesting properties, probably not worth diving too deeply here. But this just goes to show you, we're going to see these resonance structures in multiple examples. We can also depict the allyl radical as multiple resonance structures. And it's the same sort of idea where we're going to move the electron deficient center and the double bond to opposite sides of the molecule. So if we have our radical here, we can also have it over here. More resonance structures equals a more stable molecule. What does that say? If we have more resonance structures, the allyl radical is more stable than expected. Okay. I think that's what I need to say. Oh, and then I could emphasize this. If it is more stable, if the allyl radical is stable, then doing a reaction to generate an allyl radical is easier. So it's easier for reactions to occur that generate allyl radicals. All right. And what that means is that we have a low BDE. What was that BDE again? 87 kcals for every mole of this structure that we have. And so we could pump in some energy to this, do a homolysis reaction, and we'll generate a molecule that has no choice but to be depicted by one resonance structure. Okay. So I actually show a reaction here where we generate two resonance structures. Because these structures just depict the same molecule, it's healthy to do this. Now, ultimately, at the end of the day, what sort of matters when we're depicting molecules is a deep understanding of the three-dimensional orientation of the atoms in our system. So we have to understand that these atoms are going to exist where they're going to exist. When we try to depict them on a piece of paper or an iPad screen or something, we're taking a lot of shortcuts and exercising a lot of liberties. It's not just deleting carbons and hydrogens. Okay, we're drawing these lines with fixed lengths. Okay, like the way I draw it, it looks like my double bonds are the same length as my single bonds. Well, no, they're a little bit closer together, because the closer the atoms are together, the stronger that bond is going to be. Double bonds overall are stronger than single bonds. Now, additionally, another shortcoming is just going to be that you can't just draw a bunch of double lines and single lines and zigzags and expect to, have a lot of accuracy in precision. Precision is a better word. Precision in depicting molecules. Molecules are complicated, and as a result, there's going to be some shortcomings with our Lewis dot structures and our bond line structures. These shortcomings are made up for with resonance. So being able to draw multiple resonance structures will allow you to see what kind of chemistry can happen. We saw that previously with alkenes. Now we can see that a little bit with allyl systems, but we're going to look at that in incredible depth through the rest of the semester, really. So take time now, learn all the rules about resonance structures in the upcoming lectures, deeply integrate them, ask for help. I know some great books on this too that are actually kind of fun to work through, but resonance structures are sort of where it's at to understand organic chemistry in as much depth as we're going to go for in the rest of the semester. Okay, well, I'll see you next time. Have a good one, everyone.